So yeah, so we will start with some examples of isomorphism and automorphism. So as I was saying, so we have this graph here. Let's say G with the vertices 1, 2, 3, and 4, and it's a path graph, as you might remember. And what we will do is to see if there is an automorphism you can find to the graph H on the right hand side, which is having exactly 4 vertices again. Now, if you know what's an isomorphism, isomorphism basically is a bijection, first of all, right? So because it is a bijection, we know that there is a bijection between two finite sets if and only if it has the same number of elements. So therefore, first thing to check whether there is an isomorphism between two graphs is to see if there is a if if there is a bijection, to see that if they have the same number of vertices, right? If they don't have the same number of vertices, you don't have to look for an isomorphism. You can immediately say that okay, there is no isomorphism between these two, right? Then the second is that because we know that edges must be preserved, right? That every edge in the graph G, right? So if UV is an edge, then f of U, f of V must be an edge in the graph H. And similarly, what we want is that whenever UV is not an edge, f of U, f of V must not be an edge, right? So the edges and non-edges must be preserved. That is the definition of the isomorphism. So if the number of edges is different, then again we know that there is no such isomorphism between two graphs. So here again we can check that the number of edges is also the same. So then we can try to see, okay, if there is any function at any bijection which takes edges to edges and non-edges to non-edges, right? So so what we do here is just to look at several possible bijections and then see if any of them basically leads to an isomorphism, right? So here I have listed some functions f, g, h, I, j, k, which are all bijection from vertex set of G to vertex set of H, if one of them is an isomorphism or not, we can check, right? So you can start with one of them, let's say f, right? So if you look at f, so what is this function does? It takes 1 to a, right? So 1 goes to a, right? Then 2 to c, right? 2 goes to c, 2 goes to c, then 3 goes to d, and 4 goes to b, right? Now, so to make sure that it is an isomorphism, we have to check all the edges go to edges and non-edges go to non-edges. So here 1, 2 goes to, let's say, f of 1 is a and f of 2 is the AC. So AC is an edge in the graph, right? So therefore that is fine. Similarly, 2, 3 goes to CD, right? That is also an edge, so that is fine. And then 3, 4, which is an edge, goes to DB, right? Which is also an edge. So the edges goes to edges, and because the edges are accounted for, all of them are accounted for, non-edges must go to non-edges. So therefore we have an isomorphism. So F is an isomorphism. Right? Then you can similarly check G is also an isomorphism, I believe, right? You can verify. And is G an isomorphism? Yeah, G is an isomorphism, right? And similarly, you can verify that H, for example, if you take H is not an isomorphism. Because H takes 1 to A and 2 to B, right? 1, 2 is an edge in the graph, but AB is not an edge in the graph, right? So therefore, H is not an isomorphism. So this is not. Similarly, we can check I, J, K are all not isomorphism. In fact, F and G are the two isomorphisms, and you can verify the other possible permutations also will not lead to isomorphism. Right? Okay. Then Here is another example, right? So we have this graph G and graph H. And then you can ask whether there is an isomorphism from G to H. So what do you think? Is there an isomorphism from G to H or not? So if you spend some time, you should be able to find out an isomorphism from G to H. In fact, they are isomorphic. And then here there are other two graphs, let's say G1 or G dash and H dash. Right? Now G dash, H dash, are they isomorphic? Again, first thing you have to check is that the number of vertices and number of edges are the same. Right? So in the previous graph, you had 5 vertices and 8 edges, and in both cases, 5 vertices and 8 edges. So if that is not the case, we can immediately rule out. And in this case, S dash and G dash, again have the same number of vertices, right? 6 vertices and 9 edges each, right? Both of them have 9 edges. And every vertex, for example, another property you can check is that, the number of vertices of the same degree must be the same for both, right? So if there are 3 vertices of degree 2 in one graph and 4 vertices of degree 2 in the other graph, you will not be able to find an isomorphism. Okay? This is something you can try to check why. It should be intuitively clear, but one can try to check why. But now, if these are true, then suppose you are trying and you are not able to find an isomorphism, right? If you are not able to find an isomorphism, then what will you do? I mean, suppose two graphs, which whenever you look, it has the same number of vertices, same number of edges, and also let us say that all the vertices have the corresponding degrees are same and all these things, and you try to find an isomorphism, but you are not able to find it. Now, how do you prove some two graphs are not isomorphic, right? I mean, like if yes, tell me.
We have to look at the cycle length of the both the figures. So if they are same, then they are isomorphic, or else means we have to look at all the properties.
Yeah, so cycle lengths are the same need not mean that they are isomorphic. Is it necessarily true?
No, means we have to look at all the properties, whether they are the same in both the graphs. Then we have.
So what do you mean by all the properties? There could be so many properties, right?
Yes, sir.
Yeah, so yeah, it is not an easy question, right? Like, so what I wanted to emphasize is that, like, finding an isomorphism, to show something is isomorphic, you just need to find one function, right? Which is an isomorphism, right? Which satisfies these two properties: edges are preserved, non-edges are preserved. But to show they are not isomorphic, you need to either go through all possible, bijections and say that okay, each of them are not an isomorphism, or another way is to show some graph invariant is different, because if two graphs are isomorphic, then all the graph invariants must be the same, because what we are saying when two graphs are isomorphic is that just one is just a relabeling of the other. We are just naming the vertices in different way or representing it different way, but they are all the same, right? So all the graph invariants must be the same. So if you can find some invariant which is different for graphs, then that shows that they must be non-isomorphic. So that is one way to do it. And here, as I don't know who pointed out, this graph, you can say that one of them is bipartite, right? The one on the right hand side is bipartite. On the other hand, the first one, G dash, has a 3 cycle. It has an odd cycle, and therefore they are not isomorphic. So this is one way to do it. But of course, we could have two graphs which are both bipartite, right? And then having similar cycles and etc., but still not isomorphic. So here is an example, right? So you have two graphs, G and H. Both are bipartite graphs. Okay. And I have given the bipartition in color coding, right? So the white vertices and the yellow vertices, they form two independent sets. And they have the same number of vertices, same number of edges, right? So I think 32 edges each and 16 vertices. And they are not isomorphic. Now, how do you show they are not isomorphic? I think I should leave it as an exercise because it will be very instructive to work out and see whether you can actually find it out. Some way to say that they are not isomorphic. So maybe it's a nice question to think about. But I wanted to emphasize that, like, yeah. So so both of them have like 8 cycles. They have like 4 cycles. All kind of cycles are there, but they are bipartite. But still, some parameters you will be able to find if you spend some time, which are different. So they are not isomorphic actually. So take it as a question and work out. Now, automorphism is essentially isomorphism from a graph to itself. Of course, the identity is always an automorphism, right? And some graphs have only one. The identity is the only automorphism, right? Now, there are for example the path graph 1, 2, 3, 4. One can show that there are two, and one is the identity, and the other one is as depicted here, right? So the only automorphism here is basically the reflection of the path. So you just take the reflection, you get the isomorphism, and basically 1 goes to 4, right? 2 goes to 3, 3 goes to 2, and 4 goes to 1. This is the only other isomorphism between the graph and itself. On the other hand, if you look at the cycle on 4 vertices, right? Instead of path, you just add one more edge. You get the cycle on 4 vertices. How many automorphisms this have? In fact, one can show that there are several automorphisms for this. And how do you see this? Again, geometry helps, right? If you look at the picture, you see that rotating them, right, will not change anything, right? So if every rotation is a permutation, and therefore all rotations of this are going to be automorphisms, right? And then you can see that if you take reflection along the for example, if I take reflection like this, 2 and 4 are basically mapped to each other. 1 is going to 1 itself, 3 is going to 3 itself, or like this, or even like this, right? So reflecting like this with a mirror, and then like this. So any of these reflections basically keep the cycle itself. So therefore, each of these permutations are actually isomorphism. So there you can see that all the rotations and reflections, there are 8 such permutations, and each of these 8 permutations form an automorphism. Again, and that forms a group which is called the automorphism group. Then another way to look at is that basically a permutation that does not change the adjacency matrix. So if you have the adjacency matrix, you can just permute the vertices and see, like then you have to reorder the columns. But if the matrix remains the same, then again you get an automorphism. What about these two graphs? So here is a graph on 4 vertices, and how many automorphisms it has. Now this graph is complete, which means that if you take any permutation, right, any permutation of the vertices, any two are adjacent, so therefore there is no non-adjacency, right? So wherever it goes, its neighbor also goes to its neighbor only, right? So therefore any permutation, all the 4 factorial permutations are all going to right, all permutations of the vertices, right, will lead to automorphism. So therefore any permutations are automorphism. Then what about the graph below, right, which is as you see, it's a bipartite graph, and it's a complete bipartite graph. It's a complete bipartite graph, which is called K 3, 4 in this example, right? And how many permutations do you think they have? How many automorphisms do you think it has?
3 factorial into 4 factorial.
3 factorial into 4 factorial. Why is that?
Like on one side, we can exchange all the, like we can allow all permutations on both the independent sets.
Yes, if you change, between one independent set, if you change, the order, because they are all adjacent to the opposite sides, it does not matter which order they appear. So therefore, you have 3 factorial into k factorial, right? Permutations for the, and independently you can do on both sides. So therefore, you can take the product. So we have these many automorphisms for this graph. Now, what about k 5, 5, right? How many do you think it has?
2 into 5 factorial square.
Yes, so that is another thing you should notice, that you can also interchange the partite sets themselves because both sides have the same. So it is 2 into 5 factorial square. Okay, good. So now you know about automorphisms, I hope. And here is the different automorphisms of the cycle that we just mentioned before. All the permutation. So here I have just noted this order says that where the first one says that 1 goes to that number, second one says 2 goes to that, 3 goes to this, and 4 goes to this. That is the permutation. So these are all automorphisms of the cycle on 4 vertices. So every cycle of length n has 2n automorphisms. Now, today I want to spend some time to see some applications, because some student asked some time back, can I present some applications of graphs? So I thought maybe I can just introduce some questions and some examples, and I think today I will just do that, and then we will discuss something else in the next class. Okay, so graphs as models. So one of the main reasons why graphs are so much used is that they are very useful as the models representing several real life problems. So here are some examples. So one is that so you want to prove that let's say every set of 6 or more persons, you can find 3 people who have met each other, or there are 3 mutual strangers who have never met each other, right? Now, so again, I want all of you to just type your present here, just to take the present. I will keep it. I will save it and note it down. I have to figure out how to do this later in an easier way later. Okay, so here we want to show that suppose a set of people meet at a bus stop, you are standing at a bus stop waiting for a bus, right? And I'm talking about in the past, right? So you're waiting for a bus, and then there are several people standing there. And then you think, okay, among these, you might have met some people, maybe, right? Or some others know each other. We don't know. But can we always say that there will be at least 3 people who know each other, or at least 3 people who doesn't know each other? So it turns out that if there is at least 6 persons in the group, then we can always say that one of these happened, right? Either there are 3 friends or acquaintances, to be precise, or 3 mutual strangers that none of them have met each other. So how do you model such a question in terms of graph theory? Well, to represent each person, you can use a vertex, and if 2 persons have met each other, then you put an edge connecting these 2 people, and if they have not met each other, then there is no edge, right? So this basically represents the relation of friendship or like acquaintance. Now, once you have this, the question reduces to the following, that you are asking if you can find in this graph representation, if you can find three people who are or three vertices who are adjacent to each other, which is a complete graph as a subgraph, which by the way is called a clique. So if you can find a three vertex clique or an independent set of size 3, right, that they have not met each other. So you are basically representing this question as a graph theory question where you are looking for subgraphs which are either complete graphs on three vertices or independent sets on three vertices. So like if you have a representation like this, then you can see whether. So in this case, you immediately see there are three vertices which are adjacent. If this is the acquaintance relation, you have three mutual acquaintances, right? On the other hand, you also have three mutual strangers in this case, right? For example, this, and this, they are mutually non-adjacent. So therefore, we have both happening in this case. On the other hand, if you have this, there are no three mutual acquaintances, but you have three mutual strangers. For example, these three are strangers. Now, one can formally show that if there is at least 6 vertices in the graph, it will always happen, right? 5 vertices, you cannot guarantee it, but with 6 vertices, it will always happen. Now, so how do you show this, right? So I want you to work on this. Maybe it's a nice exercise. Show that, like, if you start with 6 vertices, and then you can actually use a very nice result from combinatorial called pigeonhole principle. If you are not familiar with it, please read it up. But you can use it to find a very easy proof for this. So think about this and then try to find out. Okay. So, but one can model this kind of questions in graph. So yeah, so this is what the problem says, that every graph on at least 6 vertices contains either a K3 as a subgraph or an independent set of size 3 as a subgraph. Okay. So let me.
In the previous problem, like a graph contains a K3, or can you say it's either it contains K3 or the complement of the graph will contain K3? Are those equivalent?
Yes, exactly. You can do that also. Okay. Yeah, sorry. I was just looking at the attendance. Now, yeah, so what we were saying is that the second question is that, like, let's say that a company has M jobs, okay, that they want to offer, and it has got N applicants, but now not all applicants may be suitable for all jobs, right? The jobs may be of different types. Now, can we fill all the jobs with qualified persons? That is one question that the company would like to answer, right? Now, how do you approach such a question? One way is to model it as a bipartite graph, right? In which what you do is that you represent each job as a vertex in one side of the partition of a bipartite graph, and all the persons will represent the other set and let's say J represents the set of vertices which represent the people, which represent the jobs, and A represents the set of applicants. Then an edge basically connects, let's say, a job J to an applicant A if the applicant A is qualified to do the job J, right? So now we have a graph, and this will be bipartite because the edges will only go across J to A, right? Applicant and job. And now the question reduces to asking whether you can find what. So whether you can find a set of non-adjacent edges, pairwise non-adjacent edges, which are of size at least m, right? Because an edge basically represents that one job is mapped to an applicant, and if you can find pairwise disjoint edges, if there are m of them, then of course m jobs must all be saturated, or m jobs must be already assigned to a person, right? So this question is basically finding pairwise non-adjacent edges, which are called matchings. Okay, so in a graph, a matching is basically a set of pairwise non-adjacent edges. So here is an example of a matching, right? So you have this graph. The blue edges form a matching because they are pairwise non-adjacent. The yellow edges form a matching, the two yellow edges, right? Yellow means that yellow double line edges, and then the white line edges are also forming a matching, right? But if two are incident to each other, then they will not form a match, right? So for example, this and this is not a matching pair of edges because they have a vertex in common. We don't want that. We want pairwise non-adjacent edges. So the problem is to find pairwise non-adjacent sets, and we need at least m of them. So if we can find m such edges, then we are done. And we cannot find more than m, of course, because we have only m vertices on one side, right? So the question can be answered by looking at the this matching question. So again, we will study these things later, right? Bipartite matching algorithms and all we can try to find out. Then you have the next question. Lots of airplanes today. So yeah, so the next question is that you have this few exams that need to be scheduled for several courses, let's say. And when a student is taking several subjects, right? You cannot schedule two subjects in the same day if some same student is appearing for both. So now the question is that what is the minimum number of days that you need to allocate for the exams, right? If we don't want two exams for a student in the same day, right? Now, how do you do this? Well, we can use for each course we can say that okay, we have a vertex, and then if two courses share a student, right? Then we say that there's an edge connecting these two vertices, right? So if there is some students common to two courses, then we will connect them with an edge. And then what is the question that we want to solve in terms of graph theory? That is, we want to find out, like for example, we want to mark, let's say that each day I am going to make it as a number, let's say first day, second day, etc. Right? So we can label the vertices of this graph now with the day, which means that day that course is going to have this exam, right? So each course, the exam day will be decided by the label. So now we want to label the vertices such that two vertices which are adjacent should not have the same label, right? That is what the question reduces to. And this is called coloring in graphs. So we are talking about properly coloring the vertices, right? So coloring is basically labeling in a fancy term, such that no two adjacent vertices are labeled or colored with the same color, right? And the minimum number of colors that will do this job is called the chromatic number, and that is the number that we are looking at. That will tell you the minimum number of days the exams need to be scheduled. Right? So formally, the chromatic number of a graph chi of g is the minimum k, natural number k, such that g admits a function f maps from the vertex set to the set 1 to k. So this notation represents the set 1 to k, 1, 2, 3 up to k, where f of u is different from f of v for every edge uv in the graph. And then we say this function f is a proper coloring of the graph. So the chromatic number is denoted by the Greek letter chi of g, and that is the smallest number which will do the job. So again, we will look at chromatic number and coloring in detail. We will spend some time on this, in fact. And there are several applications of coloring. This is just one of them. I mean, you can see there will be hundreds of different places where exactly the same problem can be used for. Right? For example, finding the chromatic number can be used in several situations, like scheduling for several things, exams or meetings is just one of them. Then you will see other applications in computer processor sharing, and then what is we will come to some more examples soon. And yeah, so one thing that you can note is that by the way we have defined coloring, the set of vertices that gets a fixed color will be an independent set, right? Because we said that no two vertices which get the same label can be adjacent. So therefore, that set will be an independent set. So basically, we are partitioning the vertex set into independent sets. So that is also another way of looking at coloring. So coloring of a graph is proper coloring of a graph is basically partition of the vertex set into independent. Now there are several other notions of coloring, which are basically defined for each different types of questions that we want to handle. For example, you can allow other conditions to be added, like proper coloring with some extra conditions that the subgraph induce, by let's say two colors should not form a cycle, or many other conditions. One can, this is called cyclic coloring. Then you have so many different notions of coloring. We will try to see a couple of them, maybe. I don't know. We'll see. Then you have notions of edge coloring, and we'll see that also, I think, in the next few pages. Now, here is another problem called map maker's problem, right? So basically, a map maker, right? So when you take maps of political maps or geographical maps, you want to basically give colors to the countries or districts of a country, right? Such that different adjacent countries will get different colors, because that's why we can, when you look at, you will be immediately able to see which is the border of a country and what are the neighboring countries, etc. Now, the map makers generally want to reduce the number of colors that they use, and this is for several reasons. One is that less number of colors, especially in the olden days, makes it much easier for them, less costlier, etc. But apart from that, it increases the contrast. For example, if you use, let's say, a different color for each of the countries, like if there are hundreds of countries and you use several different colors, then the contrast will be very less. And then if two colors which are close by, it will be difficult for people to immediately distinguish the border. So therefore, it is best if you use the least number of colors possible. So therefore, the natural question is, what is the minimum number of colors that will do this job, right? That I can color the countries. Now, if you assume that a map is basically a partition of the plane into connected regions, okay, so this is important. The connected region is important because if you assume that a country has several disconnected parts, then the conclusion doesn't hold. But most of the cases it will be not like that. So assuming that we partition the region into connected regions, then four colors suffice. So this was a very famous question, and in fact it was one of the most prominent questions that made the development of graph theory for around 120 years. Okay, so this problem lasted around 125 years. I think in 1871 or somebody, I think Francis Guthrie or someone, basically asked this question, and then after so many attempts and developments of several techniques were made just for proving this, and in 1976 only it was proved by Apple and Haken. Ira Apple, I think, and I forgot the other name of the German guy. So these two people proved it, and it used a special technique called discharging method. We will probably see or look at this method sometime. I don't know. I have not yet decided. And, that finally proved that actually four colors are sufficient in this case. So this just one problem took the development of graph theory for more than a century. Of course there were other problems in between, but the main thrust was this question, and there were many different techniques developed for this. We will look at one or two techniques in between, maybe depending on how the course progresses. Now, what we do, how to model this question is again to map this question as a question on what is called planar graphs. Okay. So how do you model this? So every region, of the map becomes a vertex, and two regions which share a boundary line, we make them adjacent. And now the question reduces to finding an upper bound for the chromatic number of such graphs. Right. So basically, you want to color again where adjacent vertices have sharing boundary, so that they should not get the same color. Right. So therefore, the question again, the same chromatic number question we define for the exam scheduling. Solution will be applicable in such questions also. But looking at a special type of graphs, so the numbers that turn out may be different. That's the only difference. So just a very quick look at this. What is a planar graph? We will visit this later in detail. So a planar graph is basically you try to visualize the graphs by drawing them, right? So when you draw them, you are basically drawing on some surface. So whatever the surface is. So if you take some surface S, right, then you want to basically assign, right? So assign distinct points on the surface, right, to vertices of the graph, right? Right. So an embedding is basically an assignment of distinct points to the vertices of the graph, and right, and the edges are basically simple, let's say, curves. The definition of simple curve is not that simple. So for the time being, we'll assume that a simple curve is a curve which does not intersect itself. So they are basically curves on the surface between a pair of points and which does not intersect itself. So are simple curves that edges are simple curves such that curves that join, let's say, join join the corresponding points on the surface such that no two edges share a point on the surface, of course, a point, except the endpoints. So, two edges can be basically, crossing or touching only at the endpoint. So basically, you have these vertices, right? We are talking about. Then you are allowed to, put these curves connecting them, and they can basically intersect at the vertices only, right? At the endpoints. And for example, you are not allowed to draw like this, right? This kind of a drawing is not allowed. I can do this, right? I can go, like this and all, no problem, right? So just simple curves which does not intersect itself, and they must not intersect each other except at the vertices. So such a representation is called an embedding on any surface, and if the surface is the plane R2, then it's called a planar representation. And such graphs which has a planar representation is called a planar graph. The planar graph is a graph which can be drawn on a plane without the edges crossing. It's a simple intuitive way to look at this. Now, this question is basically asking now. So one can show that the graph that you obtain from this kind of maps, right? The maps which are basically partitions of the regions into connected partitions of the plane into connected regions, right? Then such maps will always result in graphs which are planar graphs. This is something one can show. Again, these are not immediate, but one can show this. And then one can show that such graphs, that the planar graphs will always be colorable with just 4 colors. So this is called the 4-color theorem, and this 4-color problem has, as I mentioned, 125 years of history. Right? So this was open for 125 years and proved in 1976 for the first time. There were several other proof attempts because this proof used the help of computers to verify several cases. And then, even the later proofs eventually use the help of computers to verify the cases. That is another thing. So if you can find a proof which does not use computers, you will be really, really famous. So we will discuss this method, and I hope one of you will come up with an improved version. Okay. Then other applications, like for example, transportation networks, right? If you have road networks or other networks, then you can model this by the intersections representing vertices, and then the edges are going to represent the road segments connecting two places, right? And then one can ask questions, several questions on this, like the reachability questions or the distance, shortest distance. We can even assign weight to the edges to say that okay, the length of the the road is given by this weight or the time that is taken on this road. For example, when you look at Google Maps to find a route, it finds out what is the shortest route, and it also tells you the route which is the fastest, because it dynamically, it will assign the weights to this edges looking at the traffic, congestion, etc. And then, that will tell you the time, and then it calculates the best time possible. And all these things are, you done using algorithms which are essentially coming from graph theory. You have parallel computing, right? So you have multiple processors which are connected, and they need to be connected to each other so that this computing, right? Parallel computing is basically doing several parts of the problem by different computers, because it usually takes a long time otherwise, and there is so much of data to compute. So in that case, they will try to distribute the work to several computers. Now, depending on the question, the communication that is required will be different. So therefore, we need different models of interconnection between the processors. So for this, one can have several models. Of course, there are other parameters. You cannot just put arbitrary model, right? Which requires which are required. So there are several models which has been developed based on the structure of the problem and the structure of the network that we want. Here are a couple of examples. Like for example, you have the complete network where every processor communicates with each other. Of course, this makes it more costlier and more difficult to implement algorithms and all. And several questions might require this. But then there is the shared bus network where you have a single line of the communication bus, right? Which are all shared by the different processors. So this is another network which is used by for the multi processor computers. Then you have the ring network, right? How very easy to see why it's called ring networks. Then you have tree network, basically graph without cycles. We will define this in the next class maybe. And what is called hypercube network. Again, we will not discuss this at the moment. And even more fancier names like butterfly network. And I mean, this is not a very reliable representation. It's quite technical to draw this. It will take a lot of time. I just draw some parts of the network actually. It is not complete. Okay? So don't think that it is the exactly the butterfly network. Then similarly, you have what's called a wrapped butterfly network. So these are all used for different types of applications, and it comes from the properties of such graph that is being depicted here. Why it is useful for certain types of applications. So we need to study several parameters related to the structure of the graphs, right? And why they are useful for this kind of questions. So these questions, of course, we will not probably look at these kind of questions in this course, but on further studies, one can look at this. And then you have let's say radio networks where broadcasting towers, and they are basically broadcasting either television or radio, and then you need to basically assign frequencies, right? Which frequency they are going to communicate with the radio, right? So this is called the bandwidth. Now the bandwidth must be assigned to different towers, because if two towers which are close by, right, which can communicate to each other, not communicate, basically broadcast to within the range of each other, then there can be interference. Like the house which is sitting in this intersecting region might be able to see the tower A is broadcasting something with one movie, then tower B is maybe broadcasting a news with the same frequency. They will have interference, and you will see both of them mixed in the video, right? This kind of thing we don't want. So then one can convert into a graph theory question and represent as a vertex coloring question in this. But on the other hand, if you have a two-way communication, right, instead of broadcasting, then the question scenario is very different. Okay, so if you have wireless communication networks where both way communications are there, then if you have this kind of a tower basically which receives from a mobile, for example, this is a mobile phone, and then there's a tower, and then they are basically communicating, or they can basically communicate between themselves maybe also, right? Then what you need is that, for example, these frequencies all must be different. For example, if this frequency, right, and this frequency is the same, then there is a problem. Like whatever he says, I may be able to listen, right? If there is a the range is within, for example, right? Or this guy may be under confusion, like whom am I talking to, right? Or whose message is coming from, right? So that kind of things will be a problem. But apart from this, so this and this should be different. This color and this color must be different. And in fact, you can see that all these vertices, all these edges must get different colors, because they are all the different communication and bandwidth that they are going to use. But this is not sufficient. I claim that we also need all this must be also different from this, because what happens is that otherwise, if let's say that let's say A is communicating, A and B are communicating with some frequency, let's say color purple, right? Now, let's say that these two are communicating, with the same frequency. Now, if the distance, these two are in reachable distance, which means that this guy will be basically like sending back communication to this guy using the same frequency, but that is also received by this guy B. So now B doesn't know whether he is communicating with A or with this person C, right? So therefore now B might send whatever he gets from here to A, and what is he saying will be now audible to A, and similarly that kind of issue. So therefore we want all these edges in the graph that I show to get different colors, right? They get different frequencies. So this is called a distance 2 edge coloring. Edges which are at a distance 2 must get distance 1 must get different colors. So this is called strong edge coloring. There is a lot of work on this. In fact, I have myself worked on this question. Some work, in my PDF time. Now, finally, I think our time. What is the time? Okay, 12:50. Yeah. So I will just wind up with this final thing. So we have this chemistry, like where we have several molecules and we can represent molecules in different ways. Sometimes we might need multigraphs because you have these kind of connections between bonds between molecules, the atoms, that may be represented by multi-parallel lines. So you need multigraph sometimes. But then one question which is interesting in chemistry, if it comes from chemistry, is, for example, it's called the Wiener index. It's a graph parameter that is defined, where you have you look at the sum of the length of the shortest path between all pairs of vertices, which is basically represented in a molecule, in an organic molecule, which represent non-hydrogen atoms. And in this case, for example, like you have these two, butanes. Butane is basically having four carbon atoms and then 10 hydrogen atoms. But there are two different possible butanes, in that occurs as molecules. So the structure is different. One is there is a path of four carbon atoms like this. Then all the hydrogen atoms are incidentally like this. And then you have like the carbons forming this K13 structure, and then the hydrogen atoms are represented like this. Now these two have different properties because of this different type, right, of structure, and that properties can be basically characterized by what is called the Wiener index. So these kind of questions, one can look at, and there are hundreds more. We cannot spend time for that thing. So I will wind up today with this application. Maybe the rigidity. This is for I think structural engineering, like in civil engineering and all. When you basically make structural networks, you can talk about a parameter called the rigidity, like how rigid is the frame so that it doesn't collapse. And we can maybe look at this example, as a homework question sometime, right? And then how we can define a structure to be rigid and when it is going to be not rigid. So this comes in applications in civil engineering. So anyway, with that I will just stop this very short introduction to application to engineering. Probably we will not visit most of these questions except one or two theory parts which will be developed. But I hope that people who are interested can definitely take up on these things later. So with that I will stop today.